Hi, I'm Ray Weiss, and thank you for having me. Let me start by saying the following. I'm going to give you, the outline of my talk is fundamentally that I'm going to say a little bit about the history of this field, because it's not known that well. I mean, gravitational waves themselves have had a very complex history, and I'll describe some of that to you. But then I will try to also explain some of the technology. And then I want to talk about the big discovery that has been made. And at the end, I'd like to talk a little bit about the future of the field. So there's an awful lot I want to cram into this thing, and I'm a little worried about that I've done too much, but let's get started. So I got to learn all these different things. Let's see if this does what it's, yeah. Well, I mean, these are slides which are the complicated things. There are going to be many of them, and they are the history of what the field is. Now I will point to various things in it so that I can keep you abreast of where we are in the story of gravitational waves. But I'm going to start with Albert Einstein, and last year we had a big celebration. In 2015, we celebrated the 1915 discovery by Albert Einstein of the field equations. And that was a huge celebration all over the world. And what it was the beginning of a new theory of gravitation. I mean, all of us have been in high schools and probably in college have learned about Newtonian gravity. Newtonian gravity was a theory, I won't go into any of it, but I just want to say what's the difference between Newtonian gravity and Einstein's gravity. Newtonian gravity is fundamentally a theory where things, and you know of it, it's the thing that holds you down the ground, so does Einstein's theory. But what it is, it's a theory that has a force. The force is proportional to the masses of the two objects, and it gets smaller the bigger the distances between the objects. It doesn't talk about information traveling between things in gravity. But that's something when you begin to think of Einstein in 1905, he was already thinking about that. You had to worry about things having a limiting speed. And information, even in a gravitational field, has to be limiting. It can't go faster than the velocity of light. That's something that probably Newton didn't really know, or couldn't have known. And so anything that came after that, after then, had to include the idea that there was a finite speed of propagation. Now, what Einstein's theory did, and it developed out of special relativity, is the fact that it was a theory that did not have a gravitational force. It was a theory in which space gets deformed by mass, and then when that deformation has taken place, the masses, the things that are in it, move because of the deformations. In other words, space then tells mass how to move around. So it's a completely different idea. It's a geometric idea, a geometrization of gravitation. And that was the big thing that Einstein did, and I want to show you now and immediately get to the notion of gravitational waves. And in 1916, Einstein wrote his first paper on this, so that's a year later than the big discovery of the field equations. In 1918, he wrote another paper where he corrected his errors. But the most important thing is in 1916 already he described that there are certain things. He didn't describe this properly. That was the part that he didn't do, that the sources of the waves, he knew they would be accelerated masses. In that 1916 paper, it turned out any kind of motion would have made gravitational waves. But it turns out that it's only the non-spherical part of the motion that makes gravitational waves. And in his initial paper, he didn't distinguish those. And that's profound, and it was a wonderful physics error, but let's leave it go. The thing is, he described completely properly already in that paper was that they will propagate at the speed of light, these waves, and they are transverse waves. And I'll show you an example of that in a second in this picture that's right here. And they are strains in space, as you'll see. They are both tension and compression. And what you're going to see in this picture, which I'll show in a minute, is a wave that's coming at you or going away from you. And it is a thing, as you'll see, it has a very special property. And here, that's why they had to move the computer, so I could be able to initiate this little motion for you. I hope I can. Yeah. Okay, now what you're seeing there is a little frenetic, but nevertheless, it has I want to walk you through this. The red dot is pretty much where you're standing. And the motion is of spots you have laid out in space. And you'll notice something interesting about this picture. This is a picture of time-varying but constant strain across the space. And the constant strain is, remember what the strain is. It's the ratio of the separation of 2 points. Well, that's the denominator, and the numerator is the amount of change of separation. So it's delta L divided by L. And so what you're seeing here is a motion that's very large on these outer points, but quite small on the inner points. And then you notice another thing about it. It's expansion in one direction while simultaneously contraction in the other dimension. That's perpendicular to it. And that keeps oscillating. And that's what a wave looks like. And that's what I want you to imagine through the whole talk I'm going to be giving, or anybody who gives a talk about gravitational waves, because it's fundamental, okay? So strain, it has the strain amplitude is the field amplitude, and it's a constant strain in the plane wave. Okay, so now, but I just want to talk about the equations. And they're interesting equations. This first equation relates, this H, by the way, is this H is the strain. It's the change in side, the separation divided by the separation. That's the field quantity. So from now on, H is delta L over L. It turns out that this relationship is the thing that relates the amount of for the first derivative, for this the time derivative of the strain, the time change of the strain squared with the intensity in the wave, what you would call the power in the wave. The amount of power, that's the number of watts, if you want to call it, or ergs, in case that's what I use here, it's the CGS units, ergs per centimeter squared per second. That is in the wave. And you'll see this, it's a very simple relation. It's very, in an E&M, you have a very similar relation between the field quantities and the intensity. But this one has a very complicated and terrible thing. It's this constant right here. And it's over here in units, in CGS units, but it's a god-awful huge number, a monstrous number. And that says it takes, if you want to have a tiny bit of strain, even derivative, forget about the derivative, just h squared, a little bit of strain, it turns out it amounts to an enormous amount of energy that you need, or it carries an enormous amount of energy. I prefer to turn this thing around and look at how much of a little bit of strain, how much energy do you have to put out there to make that strain? And what you're finding out is right off, and this is what Einstein found out also, right away, even though he had the wrong formalism to begin with, that it takes a tremendous amount of energy to distort space a little bit. That's the thing that makes it so hard to detect these waves. It also makes it very hard to make the waves, okay? And so, for example, this is the formula that he screwed up in the 2016 paper, but it's called the quadrupole formula, and it relates the amount of power that's radiated to the parameters of the source. I won't go into all of this. But the important thing is, we'll get a very similar relationship in electricity and magnetism if you did the following thing. And it's called quadrupole radiation, and even in E&M, the radiation we always teach students about and we experience is called dipole radiation. It's radiation from accelerating charges that are positive and negative. You have both positive and negative charges. And that gives you a net field. But it turns out, suppose you did the same problem all over again using positive charge and positive charge. It turns out most of the radiation field cancels. And the only reason you see any field at all is because when a source is wiggling or it's turning around like that, you don't see the two charges exactly at the same time. That's the reason there's radiation at all. And that's also true in gravity. So now here is the thing that sort of I really want to impress on you why I went through all of this development. By the way, what I'm about to tell you, you can do for yourself. And this formula is the only one I wish you would look at hard, because I'll tell you what is in. This is if you want to estimate for yourself. How big is h if you just want to put some parameters in? And these are very lovely things in here. What it is, if you want to, from some system that is moving, and we'll get to it, and it has a mass m, this is the Newtonian constant of gravity, g, which any units you like, you have to use them compatibly, and that's the distance you are away from the source, and this is the velocity of light squared. So this quantity, gm divided by r and c squared, that is a dimensionless quantity, and that's fundamental in gravitation. That's the thing that you use. That quantity, gm divided by rc squared, is the quantity you use to decide whether you want to use Einstein's theory or Newton's theory. Because what we live in right here, right now, when you put the Earth's mass in and the Earth's distance and the thing that's holding us to the ground, that number in this thing, although you are suffering when you have to climb a mountain, it's zilch. That number is 10 to the minus 10. It's a huge, I mean, it's a tiny number. It only becomes a big number when you get to some things which are outrageous, which are like black holes, and we'll talk about more about that. That number gets close to 1 at the event horizon of a black hole. And this ratio of the velocity of the source squared to the velocity of light squared is the thing that is doing the radiating effect. Okay? So if you want to just, I've taken some examples. And that's the thing that Einstein, who would love trains, as you probably, when you read Einstein's history, that's the sort of thing. A lot of his Gedanken experiments involve trains. Let's do this now. And he must have made this calculation for himself, because in that 2016 paper, he made a very interesting statement. He said, This thing, this gravitational waves, which he had just discovered in the theory, will never have an effect in physics. And he said it very bluntly. He says, this is going to be so small, it will never have an effect anywhere. And this is what he must have done. I've asked the people who do the science papers of the Einstein papers to see if they can find these two calculations somewhere in his papers. They have not found them. I mean, these were back-of-the-envelope calculations he must have done himself once he got to having this theory. And this is, for example, two trains colliding. I mean, so you put some numbers in. It's easy to do this once you have that estimating formula for it. You say the mass is about 100,000 kilograms. The velocity the trains had before they collided probably was 100 kilometers per hour, maybe a little faster. And the whole collision, because you have to know the length of the train, it's only the locomotives, is about 1/3 of a second. That's pretty fast. And now you want to separate this from Newtonian gravity because you want to be out in the radiation zone. You want to be out far enough so you're actually seeing the radiation field, not just the Newtonian field. That's still there, the thing that you learned in high school. So you have to go out 300 kilometers away. And what the h value you get for that is infinitesimal. It's 10 to the minus 42. And Einstein must have made that number himself, and that was, in his mind, measuring a thing over a meter. You're talking about 10 to the minus 42 meters. That's what's even now hopeless. So this is the biggest thing you could have thought of in 1916 that man could have made. So you look at astronomical things, and you say, well, what binary stars were people knowing about? And they probably, and I know that people saw binary stars, and let's say, one solar mass, you stick that into here, and you say that the orbital period is a day for these things to go around each other, so that tells you the velocity that you wind up with. And they say, how far away is it? Well, let's put it in the center of the galaxy. Although people didn't know how big the galaxy was in those days. They could make it 3 kilolight years away, but okay. So still, however you do it, you would wind up with an h that in an astronomical thing with big masses is about 10 to the minus 23. That's a tiny number again, but that's getting on to things that we can now think of measuring. It was not possible to do in 1916 at all. It was inconceivable. But what you would now do is, and what Einstein was hoping, I would think, is could you, from a telescope, see that change energy? In other words, what would happen if it's losing energy to gravitational waves? Could you see that orbit contract? And that was seen later on in our century, as I'll get back to, in our century. And if you put the numbers in and calculate what the loss of energy is divided into the total energy that system has, it takes 10 to the minus 13 years for a system like that to lose about half of its energy, or 1/e of its energy. So if you were looking for a 10% change with a telescope of the distance between these two guys, you'd have to wait 10 to the 12 years or so. And Einstein, if he did, I'm sure he made a number like this. So that's where that whole statement came from, that this was hopeless. And that's why I made these pictures that are the history of the field. So the very first thing is the reason, and I'll give you now the basis of these pictures, is that I made things, it's made so that things that are blue are theory, developments in theory from 1900 to 1960. Well, there are 2 more of these slides, so you have to bear with me. And then the things that are green are observations, things that have changed because of observation, things that happen in astronomy. And then finally, the technology. And I'm not going to walk you through all of this. That's crazy. That's for you to look at. But there are a couple of places that are kind of interesting, and some of the faces are interesting. So this history from 1900, here is sort of here's when the theory became, was published in effect. And then right away, the idea of looking for black holes was part of the theory. That was Schwarzschild. We'll get back to that. But here is the first guy. He's the guy who made Einstein famous. That's Eddington, Sir Alfred Eddington. And what he did is he made Einstein famous by doing the eclipse expedition to see the bending of light. But he also did a study of relativity, and he got himself into trouble right away. And I said, look, suppose, and he knew about gravitational waves, and he found 2 things. That formula I showed you, which is not important, is coordinate dependent. Depends on what coordinate system you use. You don't get the same answer for every observer. That was very disturbing already. That's why it's called a pseudotensor. And the other thing is he noticed that when he did the calculations himself for 2 stars going around each other, stars gained energy somehow, which sort of not allowed. I mean, not losing energy to gravitational waves, and then on top of that, gaining energy. He had a terrible time with it. So he thought this was all fraudulent in a way, and he called it that the gravitational waves move with the speed of thought. That's what he thought. And in fact, there's a whole book written about this by Daniel Kennefick. It's an interesting book if you're interested in the history of science. This is going to run out. Oh, well, maybe not. OK, so that's a bad beginning. But, and then what happened is Einstein himself began to doubt this whole business. In 1936 or so, he wrote a paper which he tried to get published, which he did get published. I won't go into this. That's an interesting story on its own, and with Nathan Rosen. And they came to the conclusion that gravitational waves are exact solutions of the field equation. Didn't exist. So that already threw another pall on the whole idea. And then the whole field got more and more complicated as life went on. The thing that next happened is that lots of technology things that became very important. The sort of technology of electronics became important. But there is a period right in here, which Feynman described later on as a period when this theory became mathematics and nobody in physics paid any attention to it anymore. And that's absolutely true, because what happened was that there was not any new physics coming out of it. And so, yeah, what happened was this threshold, or the important change that happened was in 1960, when it turns out that there was a conference in 1957, right in here, when there was a conference at Chapel Hill, which then was, in fact, started by Leo Goldberg, and it began to discuss gravitational waves as a reality, and people began to see that they were real. And that was a thing that then convinced Johnny Wheeler down here and Joe Weber up there to do an experiment. In fact, they together and began to think, how would you actually try to measure gravitational waves? And that was the real beginning of doing things, but it also got into trouble, as you probably know, because what happened is that Joe Weber designed that great bar up there. His idea was that a gravitational wave would come along, stretch that bar, just in those motions that I showed you in the wave, and that would set the bar ringing, and that ringing would then persist, and he could make a measurement with PZT detectors that are around the bar. And it turns out that he, in 1969, said he had discovered gravitational waves. The whole world, I mean, there were groups, 12 groups in the world easily. Europe, United States, started doing these experiments. They saw nothing, absolutely nothing. And in fact, the whole field got discredited because of that. And so what then happened is that in about, in fact, I started thinking about it then, and in about 1972, a lot of other people also had begun to think about it, especially the Russians. For example, Gerstenstein, he was a guy working in Russia in 1962, came up with this idea himself, but then it really got lost. We never knew about it. It came up again in the 1970s, and the idea was not to use bars, but rather, could you do it by timing light between masses? That idea. Could you just time light and then see if the space between the masses got changed by the gravitational waves and see the time change? That was the basic idea. Gerstenstein had that. He had it one way, and several of us have also had it. And so the thing was, right at that point, and I'll come back to this slide again, another whole technique was developed, and it was thought about. So one way to do this is to actually, this is the sort of way you think about it. You write down the metric, which is the time. This is a space and time interval between the arrival and the receipt of a light wave at some place, and you need this. And here's the metric that a gravitational wave does. It stretches space in one dimension. As you'll see, it stretches and shrinks it in another, and then there's another polarization, as you'll see in a minute, which is turned at 45 degrees to the first one, and it does exactly the same again. So that's the metric that's used. And now here's the experiment, and that I can explain quite easily. What you do is this. This is a Gedanken experiment, a la Einstein. And what you do is you do something you can't do. What you do is you put a clock and a mass here, a very good clock and another very good clock and a mass there, and then you just do the experiment of sending light from one to the other, and you calculate the new metric. That's it. That's the metric. You have the piece that's the space that's always there. That's called the Minkowski metric. And then you add to it this thing, which is the gravitational wave metric, which is now time-dependent and has this strain in front of it. That's that new thing, that h. And that multiplies. And the way you do the calculation, I won't go any deeper into that. If you want to do it for yourself, the tricky thing here is to say the masses don't move. It's space between them that changes. That's the way to think about it. So the coordinate distance between the masses doesn't change. That's this. And the time that's kept by clocks in this particular representation, the coordinate time kept by clocks is the same as proper time by the clocks. There's nothing fancy going on. So the time does not get changed. And it's a very simple equation. You can solve it for the case of h being small, which always happens. And also, let's make the gravitational waves not move so quickly that they change a lot between the time the light goes from here to there. So that's the second condition. And then you solve for the inferred separation between the two masses, just by looking at the timing of the light. And lo and behold, you get an answer, which is that delta L over L, that's the distance between those two, is indeed h divided by 2. So that was the basic idea. I taught that in a course because that's the only way I could understand it, and shelved it until Weber got into trouble. And here's a whole bunch of people who then worked on this thing. Here is the basic idea. The idea was that now you want to implement this. You want to see how could you make a Gedanken experiment into a real experiment. And that was done here in a drawing that was done in 1972 or so. And the idea was effectively to use an interferometer. In other words, send light in, and the light comes in from here, it gets split, and then it gets bounced back and forth, and I'll talk about that a little more. And it gets bounced back and forth, and then you use tricks that people before us had already done. You then measure the time it takes light to go between here and there, and between here and there, and compare the two. That gets rid of the very accurate clock you have to do. And then what happens is you very carefully look and see, as you hold these masses, you don't let them move. You actually use a servo system, which was Bob Dickey's idea. We'll get back to that. You don't let them move. What you do is you look at the force you need to keep the light the same time. In other words, use the force that you're applying on the masses so they don't move as a signal to, and that gives you a tremendous amount of control over the system. And we use that all over LIGO. It's used probably 100 places in LIGO, that concept. So, and that's the way you can do precision experiments. That was first done. But then at MIT, we started this. And then it turns out that very rapidly, people who had, in fact, the group that did it first, MIT, we were slow. But this got around to people. And the group that did, I think, the most spectacular work in the beginning of this was a German group at the Max Planck. And here they are. And what they were working, the reason why they were ready for this, they were thinking, what should they do next? They had made a big bar, just like Weber. And they were thinking, what should be the next thing they should do? And they decided not to go with the flow and make a cryogenic bar, which is a cold bar which had less noise. They decided to adopt this idea. And they developed many of the practical things that were needed to do this. Then it turns out that group influenced this group, which was a group in Glasgow that also had been working on bar. And many of these people, I think they're all, no, the only one died is this one. All of these people are dead except, yeah, they're all dead except Riediger. No, I said it wrong. Billings is still alive. He's 100 or so. Okay. But of the Scotch group, there is Ron Drever is sort of alive. And these three are still very much in the business. Okay? And they, in fact, Ron Drever then moved to Caltech, and we'll get to that in a minute. So they are the responsible people for getting this idea into something that became real. And here is the idea then. So now, here's why I want you to be able to have these slides. I've done something here which people don't normally do. I actually show you how it works. Okay? It's a little different. I'm not going to walk through all of it, some of it you're going to have to invent for yourself. But here's a basic Michelson interferometer. Here is that distance mass. There's another distance mass. Here's the gravitational wave coming down on this. And here is a laser, and here is a beam splitter. That's a device that splits the light. And remember what we're trying to do. We're trying to keep the light. I'll get to all these arrows in a minute. We're trying to keep the light so that the time the light spends in here and the time the light spends in there, think of it as being equal, and very well equal. Because it turns out when you recombine the lights, and there's a side which is called the anti-symmetric side of a beam splitter, where the two fields that come from the two arms cancel each other. They come in, and the field flips from the reflection on this side. You'll learn that in ordinary E&M, there always is going to be a side of a beam splitter where you have a phase inversion of the electric field that hits it on reflection, and another side where there is no phase reflection. So that's called the anti-symmetric port of the interferometer. That's called the symmetric port of the interferometer. That's important in our later thinking about this. And so what happens is you make it so the time spent in here by the light and that in there is the same. Then, if it's truly the same, the light will cancel at the photodetector. So this place is dark. There's no light there. And now what happens, all the light goes back to the laser. That's where it goes. That's the symmetric side. And you can see this with some of the arrows. We'll get to that in a minute. But now comes the tricky bit. The tricky bit is that, okay, you've got no light going to the photodetector. A gravitational wave comes along, and it stretches this arm a little bit and shrinks that one, let's say. And what it does, it disturbs the condition that there will be no light coming here anymore. The cancellation isn't perfect anymore. And so now there is light at the photodetector. So in the most simple-minded explanation of this, you're just detecting more light and time-varying amounts of light at the photodetector if you have set this up the way I've described. But I want to give you a more elegant way of thinking about it, because the real development requires the more elegance. And what's really going on is, and it's the same, except it's one step more subtle. And that's why I want you to look at the slide. I'm not going to be able to explain all of this, but now let's look at these arrows that I've drawn in here. And that's a little dangerous of me. I've never done this with people before. So here is the carrier. This is the light that's coming out of the lasers, this big red thing. That's the amount of light. And it comes into the interferometer and hits this mirror. And you can see that the propagation direction is the purple stuff. And you can see here, when it goes down this way, and coming out of the laser, there's only the carrier. Once it hits the mirror, or has gone through this space, but let's say it hits the mirror, that's an easier way to think about it, it comes back from the mirror, and it has two sidebands on it. The mirror, remember, is being driven by the gravitational wave, which is wiggling at a certain frequency, at the frequency of the gravitational wave. And that causes the carrier to be reflected from this. That's certainly there. You can see that. But it also makes sidebands on the light that are at the frequency of the carrier plus and minus the frequency of the gravitational wave. And sidebands are things, that's one way to think about the Doppler shift, effectively, that's coming from the motion of the mirror, if you want to think of it that way. I like to think of it more of the space doing the same thing. And that's the way Gerstenstein thought about it also. So now remember that this is anti-symmetric. It turns out here, the same thing is happening in this arm. It hits this mirror. But now look at the upper sideband has a positive sign as it comes down here, but the upper sideband here has a negative sign. Remember, this side is being stretched when this one's being compressed. And so the two sidebands have opposite sign. They come to this point, they come and add together, and lo and behold, what happens is the two sidebands add up because of this negative sign on the reflection, and the sidebands do not get canceled as they go to the photodetector. I hope you've understood this. If you haven't, you should study the picture a little bit. That's why I gave you the picture, because the next picture is the way we actually do it. So that's the basic idea. The gravitational wave sidebands show up at the photodetector, but the carrier does not. A little bit of the carrier does, so you can detect it, but let's go on. Okay, so now here's the actual detector that we made. And this is the detector that made this is the format of the detector that made the detection. It's the same idea, but now you can see some extra mirrors in this thing. And many of these ideas come from the groups that I showed you before, okay? So what you have is, here's the basic structure, so I can remind you of the other picture. Here's the beam splitter. There is a distant mirror on one. There's a distant mirror on the other. And then now a lot of things have been added. You've added a mirror into each arm, so the light goes back and forth. It bounces back and forth. That's OK. That improves the sensitivity. It makes the sidebands bigger because you hit the mirrors more often, or you do the same space over and over again. And then what happens is you notice that there's another mirror here, which wasn't there before. That mirror is called the power recycling mirror. Remember, all the light that comes back out of this, if the times in here are equal, all the light goes back to the photodetector if there's no light going to the photodetector. And that, you capitalize on that, and you reflect that back into the interferometer effectively so that no light goes to the laser and disturbs it. And what you've done is you've made it so you've increased and made a cavity out of this entire interferometer. So now the light intensity is much larger than it was just from the laser. It could be 100 times larger than just what came out of the laser. That's called power recycling. And we did that in the initial detector. You'll see that when we get to actually the curves that come with it. And the detector that actually made the detection had another mirror, this one right here, which is called a signal recycling mirror. That's a harder one to explain. But now that you know about sidebands, it's not so difficult. Because what you're doing with that is you're reflecting not the carrier, because there's no carrier here anymore. That's been canceled because you made that time equal to that time, and there's no carrier coming here. The sidebands have been doubled. And now you take and put this in a place where you can increase and make the whole system resonant for the sidebands. So you can build up the signal on the sidebands, and that's another piece of elegance. That's why it's called signal recycling. So all these mirrors are used to make the system work. And that's the one. You need a little bit of carrier, and that's what we do. We make it the time difference a little bit different in these, a little bit. We don't make it exactly equal and opposite. We put a little bit of extra time in one so that you do get a little bit of carrier at this, so you can demodulate that and get it at the photodetector. So that's the basic idea of the interferometer. Okay? And you can ask me questions about it later, but that's as much as I can do without all those arrows. You can follow the arrows and see what I told you. But you can't do it on real time. You're going to have to do it when you look at the slide. So here, then, is a noise budget for this. This is now, what are the things that disturb the measurement? And the reason we did all these tricks with the optics is so we can get enough sensitivity so that you can get a measurement. And what I haven't told you, we can get into that regime that Einstein thought was impossible. Namely, I'll be very blunt with you, this detection we made that we made was at 10 to the minus 21 strain. That's the 2 black holes you'll hear about at the end of my talk. The best they did was make a strain of 10 to the minus 21. So what you see here is a somewhat different curve. This is now frequency at the bottom. This is frequency of the gravitational wave. And what you see here is h, but not h directly. It's the spectrum of h. Well, I'm sorry for that. And so it's h divided in units of strain per square root of hertz, square root of bandwidth. So for example, if you want to get 10 to the minus 21, here is 100 hertz. And here is a noise curve, which I'll get to describing in a minute. And let's say at this point here, which is sort of the most sensitive part of the detector, you're at 10 to the minus 23 in those units. You multiply by the square root of bandwidth, and you're dealing with a noise that's about 10 to the minus 22 h. In other words, an RMS strain of about 10 to the minus 22 for this system. So now what are the components? And that's what I wanted to show you. Here are the things that come and disturb it. What makes it so that you can see this? This is the sensitive region is right here. And this is for the first detector, and we'll show you at the end for the better detector that made the detection. It's not very different, it's just better, but the ideas are the same. So in here, this thing, what's called shot noise on this side and called radiation pressure on that side, is we call the quantum noise. In other words, this is the thing that would lead to the same thing in this system as the Heisenberg microscope does when you study quantum mechanics. Okay, so in other words, here is how well you can measure the phase. And here's the fact that you have photons hitting the mass and pushing the masses around. That makes noise. That actually physically pushes the masses around. And if I have time, I'll show you that. Now, so as you increase the power into the system, into laser power into the system, this gets smaller, but this gets larger, the radiation pressure noise. So there is some optimum. And then there are other noises. The one that's most troublesome to us, of course, is seismic noise. That's the noise of the earth shaking. You live in a place right here where the earth is shaking by about probably here in this building by about 10 microns, which is sort of the size of your, well, 1/3 the size of your hair. That's much shaking going on, certainly in a city building. And so here we are at 10 to the minus, that's 10 to the minus, let's call it 10 to the minus 5 meters. And what we're asking for is 10 to the minus 18 meters. So we got to do a hell of a job to get down to this. So that's one of our biggest problems. You'll see how we do that in a minute. Then there is the fact that everything is at room temperature. And even though the mirror, everything is beautifully hanging and suspended, it's still the fact that at 300 degrees, there are excitations in the thing that are called thermal excitations, just like people see under a microscope, a thing called Brownian motion. And so the mirrors do that too, and so here is the noise from that. And then those are the big terms, and here's another piece, that's the thermal noise. And then finally, here is sort of why it costs so much to build LIGO. It's because you had to get rid of the gas that's in those long 4-kilometer tubes. I didn't tell you that. That's why the tubes have been made 4 kilometers, because we're measuring a strain. And remember, a strain is delta L over L. If you can make L very large, delta L gets progressively larger. And that's where the measurement fits, that's where the measurement technique hits the reality. How small a delta L can you measure? Not the L. How small is delta L that you can measure? So you make the thing longer, and that way you win right away. And this is all, I should have said, this is all for a 4-kilometer system already. And so now, here's the remaining, that's the noise that made things expensive. You needed to evacuate that. And then here's a noise which is the reason why, and I'll explain that to you in a second, why one wants, if you want to improve this whole system and go to lower frequencies, you want to build this in space. And this is a noise which is not so obvious. It's a noise that, although, and let me just quickly say, you can do a very good job of getting rid of seismic noise because you have a wonderful reference. It's called the inertial frame. Newton told us all about that. You can always measure your motion with respect to the inertial frame. And you use that as a way of getting rid of the noise of the Earth's accelerations. But you can't get rid of this noise, the noise that there are waves running in the Earth. And they are things that cause the acceleration, but they're also causing compressions of the Earth. And so, for example, if that lectern is a mirror, and here is a seismic wave coming along, and it changes the density here, that mirror gets pulled to the Earth, to this side, because of that change of density. And those make gravity gradients, we call them. And that's this thing right here. And that you can't get away from. You can't shield that. So we're stuck. And there are ideas we have, but this is fundamentally one of the limits. And you don't have that in space, because there's no medium that's carrying acoustic waves like that. So this is the basic geometry of the noise curves, okay? And that's what the basic idea of the experiment was, to get everything down to that point. I don't think I have time for this slide. If you want in the questions. I will show the slide and explain it. This is the noise, if you really go in detail and try to explain what the radiation pressure noise and the phase noise comes from the quantum theory. I'll just say this much about it to entice you. It is the quantum fluctuations in the radiation field that are part of, that make the quantum noise. Something that you have to take into account of, and people are thinking of ways of getting around that. So the next big step in this thing, was, and now we're up to 1960, and I think this is petering out again. What happens is that what we were thinking of is here's 1970 when that whole business I just described to you got started. But the next big venture was to try to figure out how you would make such a thing large enough so that you could make detections. And so a study was done that's called the NSF report, which was then a thing which said how much might it cost and how would you do it to make a thing that was, instead of a tabletop thing, was as big as a 4-kilometer system. And that's when this thing turned from small science into big science. And there was no way out. We had to do it. There was no way to get the sensitivity unless you made it big enough. And so then what happened is that right here, there was a study done. The NSF got started on it. They were very cooperative in doing this. But then we didn't know internally, the people of us who were running this thing, and that's Drever and Dave, Kip Thorne and myself, how to do it. That's fundamentally the problem. We just were not clever enough to make a collaboration that worked well enough. And so what happened is that, and here then is, well, we had people study this thing, a group studied this, people who are not in the field who gave it very, very high recommendations, but they said, get yourself a single director, and that was done. The first director of the project was Robbie Vogt, and he pulled a bunch of screaming physicists together and got them going together. We wrote a very good proposal to the NSF, and that got the project going, but it really didn't get it going. What happened is we had a terrible time getting it through the science board and everything else, and eventually we got a real leader, which is Barry. And he had done this kind of thing before. He knew enough physics. He knew how to do it. And that, we are eternally grateful to him for this. And then there are other directors that followed. And so here then, I think the last thing of these slides I'll show you then is that here's the time in this timeline that's now run over this long time. Here's where the detection was made. Okay, so it's time to talk about the detection. I think that's the next thing, I hope. Oh, and the next thing is really a network. And what happens is that we will develop this network. What you will see, and I'll get back to this at the end of the talk again, is that in order to find out where the sources are on the sky, once you see something, you can't point these detectors. You have to do it by timing. The timing between detectors, that's the way you do it. And I'll get to that again when I tell you about the discovery. But you have to have a network of detectors around the world. And what now is happening is that here, there was the two that were built in the United States, these big 4-kilometer systems, one in Louisiana, another one in Washington State. Very soon after that, there was built one in Italy, which was a collaboration of the Italian group and the French group, and then a group in Scotland joined it. And that is another detector that sits near Pisa and in Italy. And those 3 detectors have made runs, and you'll see what they look like. But unfortunately, we'll get to that. This detector was not running when the big discovery was made. That's because they were fixing things. We'll get back to that. And then there are new detectors being built, one in Japan, that's in the Kamioka mine. And that's a place where they hope they can get around some of those gravity gradients. And then there's a detector that has a long history, which we'll get to, but that was a third detector LIGO had in its Hanford site. We had 2 detectors in the same envelope, and the thought was given by J. Marks and others, who was this third detector of the third director of the site of the project, to why not give it to the Indians or maybe the Australians to get more spatial distance between, so you have more separations and you can do a better job of pointing. And so that will happen. Now the LIGO India thing is going to happen. All right, so now let me quickly show you how the progression of the sensitivity of this worked. And now we're getting into somewhat more into the details. What you see, that top curve, is the red curve, is the very first run that we made. It's Virgo's first run. And what you're seeing in this thing is frequency. It's very much like the theoretical plot we had, frequency versus strain. And so you have an idea. Here is 10 to the minus 25 in strain per root hertz. The next thing up is 10 to the minus 24. And you can see that what's now is superposed on this is real data, which is the fuzzy stuff that's up there, and then projections. And the very first thing you see is the top curve is the red curve. That's the best that Virgo ever made. and that's why they're rebuilding. The next one down is the curve that LIGO had for many years, and we looked with that purple curve, and we saw nothing. We saw a very good nothing, meaning we really didn't see anything. And there's a significance to that statement. A lot of people see things. It's bad if you see something, because that makes a lot of trouble if it isn't real. And that was, we saw nothing. It means we did the experiment well. I overstated it. We saw nothing. We shouldn't have seen anything, okay? And it turns out that same technology later was applied, and that's the green curve, which is the one that is the advanced LIGO curve. And that is a real curve. That is, in fact, the performance of the detector that made the detection you're going to hear about in a few minutes. Now, the curves that follow, you can see something already in that curve. That turquoise curve, which is below the green one, is where we ought to be with all the things we have. So we know we have a mystery noise. That worries us, especially at low frequencies. We don't have, right about there, if you go up to the turquoise curve, you see there's a gap between the green and the turquoise one. So there's gaps. But there's an enormous improvement that was made between the purple and the green, especially at low frequencies. And that's the region in which the detection was made. But we have more to go with the stuff that's already there. Here's what we predict we ought to get when we get done with this thing. And here are ideas I'll talk about at the end, which are improvements that are quite different yet, and improvements on the whole idea. OK, so that's sort of the history of the performance of this. What were the big changes that were made were, I think I may just say it, and this is one thing that may be useful to people in the room. And one of the big changes that was made to improve the ground noise isolation. And what that does is we use seismometers to measure the ground noise, feed back on it, just like Bob Dickey taught us to do, and makes it so that you can null out the ground motion by sort of feedback motions. And it's the same thing as people when they have noise-canceling headphones. It's the same idea. So, OK, now let's get to the detection. That's actually quite an intricate topic. And what are the criteria for that we detect something? These are important things to know in order to sort of sense whether we really saw something. And it's something very much on our minds. And that is, did we see something at both sites? And then at each site, that's important, we see the same thing within 10 milliseconds at each site. The other thing is that you have all sorts of sensors which sense the environment, and those signals, whatever you see that you think is a gravitational wave, should not be seen in these. These are sensors of the environment around you. And furthermore, there's something like 100,000 signals that come out of the detector that are measuring things like how well the mirrors are pointing, how well the lasers stabilize and stuff like that. And there should be no disturbing signals in those either when you think you've made a detection. And so that's all part that people who did more junior experiments earlier on couldn't do. This is one of the reasons it turned into big science. There's a very well-instrumented system that can do this. And here, in fact, is the discovery. And here is this is what we saw. This is time on this axis. You can see what it is. It's about 0.2 seconds, maybe 0.3 to 0.45 seconds. Here is a thing we saw at Hanford, and you saw this motion. And in the output of the interferometer, you saw in the blue, you see the same thing at Livingston. Here they're superposed on each other, but displaced in time by about 7 milliseconds. In other words, this signal that we see here is a signal that came from the south. It hit Livingston first, then it hit Hanford within about 7 milliseconds. So it is something that's going close to the velocity of light. We think it's the velocity of light, but that's not a precise thing that comes in the end result. Then, superposed on this is now the calculation. Once you do this, you see these signals. You can calculate a mass. You get that from different parts of it. You can estimate some of the parameters of the source. And you can then make a model of it. And this is the model. And the model can be done in two ways. One way it's done analytically, which is this gray line that's behind there. And the other one is a line which is done from numerical relativity, which is using computers, Einstein equations on the computers. And this now is the residual, the difference between the computer calculation and this data, right? And that's sort of white. And that's true at both sites. Now, the thing that you'll see in a minute is that this is a curve that has sublevel oscillations that are growing in amplitude. We'll explain to you what they are in a minute. But they have been filtered by a filter that looks like this. This is frequency, and this is the filter. This is one, and so it's cutting out. This filter is like a bass control on your audio set and a treble control on your audio set, and you're killing the treble and you're killing the bass. And then we did that deliberately because we want to be able to see the signal. This is a signal we see directly without all sorts of fancy signal processing. So that was very important to us because we put it through a filter like that. And that was something we didn't expect. And at the bottom here is the same thing in frequency. In other words, this is frequency, and this is the time, and this is the frequency content of the wave. You see how it goes. It goes from about 30 hertz up to about middle C. And that's true at both sites. So that was our big discovery, and it knocked our eyes out. I mean, we didn't expect something so big right away. And here is the explanation of it. Once you do the modeling and you fit it, you see two black holes. They weigh 30 masses each, about, and they are going around each other. This is sort of an explanation of the waveform. They get closer, they get faster. At this point, they're getting so close that they're about to merge, and then there's a new black hole formed. And we did not see this as well as we would like, this little piece right here, and hope on other detections we will see it. And that is the ring down of the space. As the event horizon forms around a new big black hole, space rings a little bit. And the reason why is that it takes velocity of light times for the event horizon to form properly. It's not, if it was formed absolutely smack on, so the black hole and the collision was actually spherically symmetric, you wouldn't get this, but you do, because it's coming in off axis a little bit. So here's a sort of a wow number that goes with this. This is the time again for this collision, and this is here's the relative velocity and velocities of light, and you can see that in the green curve here. It's going, and this is velocities of light. So here are two things, the size of 30 times the mass of the sun going at about, 0.6 of the velocity of light. That's sort of amazing. And then here's their separation. That's given on this axis here. And they're getting closer and closer. That was really an enormous discovery. And it's, of course, made quite a stir. Let me show you how we detected it. The way we did it is we do it two ways. We did it by cross-correlating the two detectors, the Livingston detector with the Hanford detector, by just cross-correlating them. And that's what's shown on the right. And you can see what that cross-correlation looks like. Here you can see the cross-correlation product squared. You can see it. One signal, that's the lower one, the red one's moving toward the blue one, and when they coincide, you'll see a significant signal-noise improvement, or the signal improvement, there it is. But that was the one way, but that's not the best way. But already with that, you could tell that we had a detection. Here, doing that same process here's signal noise, and and this is the number of events we saw as a function of the signal noise. And here is this event. It's way out here. It's a very rare event. It's out a place where it's so you have, it's 100 million, about 10 million years before you see this. The apparatus itself generating such a thing. I'm being a little loose there, but it's of that order. The thing was better seen in something called match filtering, which is where you actually, once you know a little about it, you have a whole set of filters with different masses and different spins and different distances and so forth, but mostly spins and masses. And you play them through. It's a very expensive thing for computation. And you play them through the system. And you see when is the signal that you have optimized against the theoretical waveform. And that's what this is. And you can see it gives you a different statistic. And it's the way actually the parameters were found. You can see that again. It's now on the bottom of that. When these things collide, the theoretical one, which has no noise on it, whereas the other one has the instrument noise, you see a much more well-defined signal. And that's, in fact, how all the parameters that we published were measured this way. And you can get a false alarm rate by assuming that every little time interval of the instrument, all the time it was running, is an independent measurement over the times that are longer than the waveform that you see there. So that's, in fact, how we get the false alarm rate. And here are some curves for that. I don't think I want to go through all of it, but it shows something interesting. Here's sort of a distribution for the masses of the two initial stars that come together. They peak at 35 and 30. This one here is just, what's the distance away? And it turns out it's a distance away plotted against the inclination angle of the orbit. And that, of course, changes the amplitude. Once you know once you know what you're looking at, the theory gives you a very good model. And that you're effectively testing the theory along with this measurement. And you find that the thing is about something like 400 megaparsecs away, or so 1.2 to 1.3 billion light years away. And it has an aspect that's close to 90 degrees. It's almost face on to you. And then here is the thing which is quite disappointing, but at least the best we could do with only two detectors. Where in the sky is this? And you see this great big banana. And that banana sort of is, and we set people on to looking. We sent telegrams out to tell people where it might be. Here is the attempt that was made by people with electromagnetic instruments. We gave them a warning where these are, and they tried to find something. They found nothing. And these are the patches over which they looked. This is a map of the sky in a funny projection. But it's a declination and hour angle. And they saw nothing. On the other hand, the neutrinos, here's from the South Pole, the ice pole experiment found detections. But here's the error bar that that we gave them. This is a different projection on the sky, and they saw nothing at that time. There's one group of people who thought they did see something, and that's the Fermi telescope, the gamma ray telescope, and I'm not sure that is a trustworthy thing. So once we have this, we can look for other things. And I thought that was the idea. Here's a whole list of the kinds of sources that we, in fact, expect that, and this is the thing that's different over those 100 years between now and when Einstein first thought of it. People began to find black holes. They found neutron stars. Certainly, that's what we saw. We had really been planning on finding neutron star binaries. That was the thing that was actually we had been planning on. We were probably going to see those because we know about them. We didn't know how, we knew how strong this would be, a black hole, but we didn't know how many there were. That was the big thing that was discovered. And then here are the other things, these things which have very low duty cycles. Supernova, for example, would be a wonderful source to find. They don't happen but once in 100 years in our own galaxy. We'll wait till the next one. And then this business of black hole normal modes, which is that ringing that I told you about. We haven't really seen that. And then there are various things. For example, there's a very active search going on every time we run to look for things which are constant signals. A pulsar. We know about pulsars. We know where they are. We know their frequencies, and we know their period derivatives. And what they are, you're looking for a pulsar that has been squished by its magnetic field. So it looks like a wobbling football. And the reason for that is that the magnetic field of the pulsar and the spin axis of the magnet don't necessarily coincide. It's exactly the same as with the Earth. The Earth's magnetic field and its spin axis don't coincide either. And the thing that's looked for over and over again and would be extremely exciting to find would be something that comes as a cosmological background. I mean, unless all the models are wrong, that's unexpected. But what's certainly going to be seen is just what are the foreground sources averaged over many. Okay. This then is, again, that curve, which I just want to quickly say there is ways to go. We hope to, with this instrument, get to an H value and this with about the blue. Here are ideas that people have for what you can still do and make the instrument better in the 4-kilometer system that we now have. And here are ideas that both in Europe and in the United States have for making the next, what we call the 3rd generation detector. And these are huge advances. And they could take this whole field into cosmology. And that's something to look forward to. And in fact, here's a very beautiful picture of showing you what localization does. This is just having more detectors. Here's sort of the error bars on the sky from a neutron star binary with a signal noise of about 8. And this is the noise you have on the error in position over the sky. For that, if you have Hanford, Livingston, that's those two the LIGO detectors, and Virgo actually running, that would be already quite wonderful. And if you now add to that India, which is, you get something that looks like that. So that becomes to be something that you could then give to astronomers and say, please look in that error bar right there and see what we see if you see something that's there. So here then is sort of the real future. The real future is that here is now the gravitational wave frequency, and here is H. Now H as an RMS value, and here's us. We now made a detection, and we're at frequencies that are around 10 to the 4 hertz down to about, well, 10 hertz. I hope we get to 10 hertz. So there we are at this point. Here is a space. It has a complete, this is if you put the LISA detector up, you will cover a completely different bandwidth, different sources. Again, black holes. And being most important, but you also see white dwarf binaries in our own galaxy. And this then is between minutes to, well, from minutes to hours. Then there is another technique which is called pulsar timing, which is just looking at a bunch of pulsars all in our own galaxy and watching how the pulse rate changes as a function of time as the gravitational wave moves through our galaxy. And that's something which will, a very promising technique. People have been working on that for a while. I expect that this is going to give very interesting results. But this is the one that's nearest to my heart. That's only because of my background. This is trying to look at the background radiation that comes from the moment when the universe got created. That's a very exciting thing. It looks at the cosmic background as to look at the polarization of the thing that is induced in the cosmic background by gravitational waves that come from the beginning. Let me leave you with that. This is the summary. Anyway, so we've made a detection on Earth of gravitational waves. That's now known. We have a consistency with the Einstein field equations, which is sort of amazing. In the sense, not that we did such a precise measurement, but over the size of the strength of gravity, we now know that Einstein field equations are good from strengths of 10 to the minus 16 to about 1. That's a fantastic range. And you know? And then we know now that the universe contains black holes that collide. We didn't know that beforehand. And there is now a pretty good guess that there are more black holes than we thought. And now what we have done by this is we've opened the field of what we really wanted to do in the beginning, which is gravitational wave astronomy. Thanks.